Back in November 2014, the city of Chennai was flooded. There was a tropical storm. The entire city was underwater and there were wide rains across the state of Tamil Nadu. The tropical storm named Nilofer not only left the city of Chennai in shambles, the torrential rains that accompanied before and after the cyclone, after the landfall of the cyclone, managed to flood the open wastewater treatment plant at our Denim Crossing unit, which was 400 kilometers away from Chennai. We contained the flooding inside our factory pretty well. Wherever there were excess rains, we were able to store water in various ponds, except for a leak of about 50 liters of water out of our effluent treatment plant. Yes, just 50 liters of water leaked from our open wastewater treatment plants. The wastewater treatment plants had a capacity to store 10 million liters of water. The plant was also designed for a normal pass-through or treatment capacity in excess of 1 million liters of water every day. So it had 10-day storage, 1 million liters of treatment capacity, 10 million liters of storage. The small leakage made the authorities of Tamil Nadu Pollution Control Board issue us a closure notice. We were asked to close down, shut down our factories, shut down our operations for 2 weeks till we rectified a defect. What was the defect? It was just a simple overflow from the plant, flooding. But thanks to this closure notice, it was a blessing. We think it was a blessing for us. It made us to think. It made us to think, why send so much water to the effluent treatment plant? We had two options. One, cheat on water treatment, or just innovate, and send less water and keep your effluent treatment plant empty and idle. We took the second route. How to reduce our effluent treatment capacity, pass through every day, how to keep our effluent treatment plant empty, and how to protect ourselves from any such future incidents. And here began an idea for water accountability on the machine, which led to water sustainability. Hi, I am Srihari Balakrishnan and a water sustainability mafioso, and I'm going to talk about water accountability and how we've innovated on our water treatment. How our perception about wastewater has changed over the years, and why we think today wastewater is nothing but pure gold. So let me first state the end objective that we achieved. We had 1 million liters of treatment capacity, we had 10 million liters of storage. What was the end objective we achieved today? We brought it down to treating just 50,000 liters per day. Yes, instead of treating today 1 million liters of wastewater, we are treating only 50,000 liters every day. A 95% reduction in volume of wastewater treated in our open effluent treatment plants. 95% reduction, 1 million liters brought down to 50,000 liters per day. To get this from 1 million liters to 50,000 liters, let me tell you how we understood what we did, how we worked before, and how we changed the way we work. How were we working before? We were working before as follows. In any textile or leather processing industries, there will be a lot of wastewater streams coming from different parts of the machine, from different processes. Our plant had 50 streams. A typical plant will have anywhere from 50 to 100 streams of wastewater streams. Fresh water will be given to all these areas, and then from which wastewater will be squeezed out. Dyes and chemicals use water as a transfer medium. Dyes and chemicals are added to fresh water, applied to fabric or leather, squeezed out, and the water will reach a homogenization tank. All this water is then consolidated. So some streams will have high pH, some streams will have low pH, some streams will have high temperature, low temperature. So all these, some streams will have dyes, some streams will have color. So the 50 streams will consolidate and take it to a homogenization tank. What we did was study first each of these streams separately. The high pH water stream separately, the low pH water stream separately, the high temperature water stream separately, the water with color stream separately, the colorless stream separately. Some streams will also have dyes in exhausted chemicals, because when you apply dye, the dye has to exhaust itself onto the fabric. The remaining dye will get washed away. Only 60% dyes, 60% of dyes will get exhausted onto the fabric. The other 40% will go down in the wastewater stream. We were homogenizing all these streams with different and varying properties. Some of these streams will have a combination of 2 or 3 properties. For example, the indigo dye stream will have indigo in it. pH also will be high. It will also be high temperature. So we studied these streams, for some streams for 1 year, some streams for 18 months. Some streams we continue to study even today, because we need to find solutions for all these wastewater. We need to find use cases for these wastewaters. We need to find fresh usages. We need to convert this wastewater streams into good use streams. What we found in these streams is that there was a remarkable consistency in the properties of these streams. The pH was within a certain bandwidth. The temperature was within a certain bandwidth. If there was dye in the stream, the residual dye had a certain milligrams or certain parts per million, and it was within a certain allowable range. This made us to start thinking about the use cases. First, the consistency itself was a revelation to us. The consistency, we thought, there will be big fluctuations, but the consistency itself was a revelation. The second thing was, each of these 50 wastewater streams mentioned, the properties we started jotting down, we started noting down, started figuring out. Let me give you an example of how we did it. The indigo washwater stream, we found that there was indigo washwater in it. It had a very large volume capacity. It had a high pH, a pH of around 12, and also high temperature, in its 60 degrees temperature. We figured out that we could, through innovation, both chemical separation and mechanical separation, we could take the indigo dye into a separate concentrate. The high pH stream, with the temperature, we could take it out separately. What we did was, we reused the indigo dye stream back into the process. We recovered all the indigo dye that was going wasted back into the process. We took the high pH water to fabric scouring. So we today became a zero indigo waste company with a dye uptake of 90%. 60% dye uptake became a dye uptake of 90%. Now that the indigo dye was removed, there was no color in the second stream. We reused that colorless, high temperature, high pH wastewater to scour our fabric. Fabric scouring happens at high temperature and high pH. So what we did was, we removed the indigo dye, we were able to reuse. Did we stop with this? No, we did not stop with this. Typically, wet scrubbers are found in most fabrics. For the high pH stream, we found a second usage. Wet scrubbers, what they do is, the exhaust gases are first wet scrubbed with water. The smoke is exhausted. We will wet scrub it. This wet scrub is to remove any toxins in the smoke, like sulfates and carbonates, and capture them as sulfuric acid and carbonic acid. And there will be more other kinds of acids. We figured out that wet scrubbing happens more efficiently using a marginally high pH water than a normal or low pH water. In an acidic water, wet scrubbing doesn't happen. In a normal pH water, it turns acidic and the pH goes down to 5. In a high pH water, there are more hydroxyl molecules in the pH water. And fusing of the toxins happens better. Sulfur dioxide toxins, fusing with water, carboxylates fusing with water happen. And our scrubbing efficiency went up from 70% to 95%. So what we did was, we take this high pH water after fabric scouring or washing to a wet scrubber. So 1 water, indigo dye, fabric scouring, went into a wet scrubbing. 1 water, 3 uses. 3 freshwater streams got reduced to 1 freshwater stream, and 1 wastewater stream was used 2 more times before it was sent to the effluent treatment plant. We continued our research, trial and error, on all the 50 different wastewater streams, one stream at a time. And we have today reduced the number of streams going to the effluent treatment plant, to the wastewater treatment plant, to 10 streams. 10 wastewater streams are today homogenized and treated. We continue working on it. We believe that we can reduce this further to 5 or 6 streams. From 10 streams, we think we can bring it down to 5 or 6 streams. Today, 1 million liters of wastewater treated has come down to 50,000 liters of wastewater treated per day. And we think we can bring it down to 30,000 liters per day. 6 years of research, 500 million liters of freshwater drawdown reduced, 250 million liters of wastewater not treated, not a gram of indigo dye sent to the wastewater treatment plant, 90% indigo recovery, 35% less indigo consumed for the denim for the same shade of dye, thanks to Cyclone Nilofer, thanks to the closure notice issued to us, thanks to our innovators, each one of who is a Chief Sustainability Officer. 400 of our factory members are Chief Sustainability Officers today. Today, looking back, we are very happy about what we did. We happen to be the world's only zero solid discharge, zero liquid discharge denim plant. We happen to use only 6 liters of water to make a meter of denim, as compared to any other closest competition, which is 60 liters to 120 liters to make a meter of denim. Just imagine what the entire textile and leather industries thought on these lines. How much usage of fresh water will get reduced and how much wastewater will get reduced. How many use cases will be there for wastewater streams. How much dyes and chemicals will get reduced. How much electricity to pump and store all this amount of water will get reduced. This is total circularity, total sustainability. I would like to close this with one statement. The amount of fresh water we reduced can be used for drinking water purposes for a town of 1 million people, 10 lakhs. If just 100 denim factories did it, 100 towns, each of 1 million people will have drinking water.